Hello, my name is Joshua Hammond, and this is Process Dynamics and Control. In this module, we're going to simulate a step test with the Temperature Control Lab. Let's briefly discuss what the Temperature Control Lab unit is. Here we have an Arduino Uno board with our Temperature Control Lab unit on top of it. You can see on the right is the inlet for the power, and on the bottom left, where we can't quite see it, is the inlet for our control to the USB computer. For any control system, we need a sensor, an actuator, something that we actuate, and a controller. Here our computer will act as the controller. We have a heater that will be our actuator, will turn up or down, and we have our sensor that feeds back that information. It's actually a thermistor if we want to be technical. With these three units, we're able to control independently temperature 1 and temperature 2, shown here. Let's now discuss what a step test is. On the bottom graph, we can see a jump from 0 to 1 right before 2 seconds. And we see the resulting change in those two lines on the top graph. This is what we normally call a step test, where a step in the input changes the output. And as we go on in this course, we'll discuss a lot more of the dynamics and what we can learn from the dynamics. Let's first focus on setting up this system, and then we'll discuss more what we can learn from this system after we have it set up in MATLAB. Our goal in this live script, as I mentioned before, is to perform a step test with the Temperature Control Lab. We'll also perform a step test with a simplified dynamic model of the Temperature Control Lab and compare the differences. Let's take a look at that simplified model now. Here we have tau, which is the time constant, or how long it takes to actually have the full change, multiplied by the derivative of temperature with respect to time, is equal to the difference of the ambient temperature and the temperature of the control lab, plus the gain times the heater setting. The gain is what converts the heater setting to an actual value, here degrees Celsius, or a change in temperature. Let's take a look now at the function we'll set up to simulate it before we actually do it with the Temperature Control Lab. Here we have our function. The change in temperature with respect to time, dt, is equal to simulated TCLab. And we have a tilde since we don't need a time point. We have temperature, and we have U, which represents our heater setting, or an input. We have our constants, tau p, ambient temperature, and the gain. Then we have our derivative equal to all of our right-hand side divided by tau p, since we need that all on one side. We need the derivative term isolated, I should say. Let's now go back up. We're going to look at how we're going to simulate this now. First, I always include the CLC clear all close all just to make sure I don't have any conflicting processes. Then I have a try-catch loop. This is nice with the Temperature Control Lab, so if anything goes wrong within the Temperature Control Lab, the script doesn't shut off with an error. Instead, it just progresses to the next thing. Here, the catch portion only has lab.off and clear lab, so that we make sure that the lab closes properly if something happens. Within the try portion, the portion that happens if nothing goes wrong, that's the only portion that happens. Well, first I'll initialize our storage arrays. So we have T1 for our temperatures of heater 1 and our time points. Then we connect to our Temperature Control Lab with a lab equals TCLab. We set the heater setting to 50, and then we use tick to start our timer. Then we loop through each time for the length of times. Within our loop, we assign the temperature measurement and the time measurement using indexing. I especially like the talk used here. I think it's just really kind of fun to use tick talk to start off our time. Tick will start the timer and talk will read the timer at any given point. We'll pause for 1 second and then we'll plot our measurements up until that point. Now let's take a moment and let's look at our Temperature Control Lab and watch what happens. As a final step, we're going to simulate this process with our simplified model we discussed before and compare it to the graph we just created. We scroll down. We have our simulation code. First, we make time points. Here I'm going to simulate from 0 to 350 to make sure I get all the time points. Next, I'm going to simulate using ODE 45. Within ODE 45, we have an anonymous function that returns time and temperature using the sim TCLab function before. You'll notice that in place of U, we have 50, since from the very start our heater is going to be set at 50. We give the argument for time, and then as an initial condition, we give an ambient temperature of 23 degrees. If we scroll down, we'll then plot both of these. A plot with both time and T1, which was our temperature control lab, and then T and then capitalized T, which is our simulated line, our line using just ODE 45. Next we add our axis labels and our data labels, and then we look at the plot. Here we have the blue line represented our simulated data from ODE 45, and our red dots like before from the temperature control lab. On the x-axis we have time, and on the y-axis we have temperature in degrees Celsius. As you can see, our simulated temperature is higher than our actual measured data from the temperature control lab. One thing we'll note through this course is as we add added complexity, we try to get a better model. Another thing to note is the magnitude at which the temperature rises. This is one of the many points of a step test. As we look at the magnitude of our step input, from 0 to 50 for the heater for example, and the magnitude of our output, or the change in the temperature, we're able to develop heuristics that we'll use later on in control. This sums up our step test with the temperature control lab. If you have any questions, feel free to leave a comment below or look on the course website below.